So in this problem, we have a car with a gross weight of 5,300 pounds, and it's parked on a street with an 8% grade, as shown in the figure below. Find the magnitude of the force required to keep the car from rolling down the street, and what is the magnitude of the force perpendicular to the street. So let's take a look at the solution to this problem. So what we have in this case is the black vector is our force of gravity that's pulling straight down on this car. And what we want to know is the force required to keep it from rolling down the ramp would be actually the vector projection of gravity onto a vector that's parallel to the plane on which the car is sitting. And so what we need to do first is to figure out what is a vector that would represent the direction vector for the plane. If we want to just have that vector be a unit vector, which is pretty much the easiest thing to do, then we can say that the vector for the plane is going to be, the first component is just the cosine of the angle that the vector makes with the horizontal. The second component is our sine of the angle that the vector makes with the horizontal. And so in this case we have the cosine of 8 degrees and the sine of 8 degrees. Now, because of our Pythagorean identity, where we have cosine squared of an angle plus sine squared of the angle is 1, that tells us that our vector P will be a unit vector. Now we remember our formula that if we have one vector V and we have another vector W, and we want to look at the vector projection, so the vector that's as much of W in the direction of V, then what was our formula, necessarily forgetting that? That was going to be the projection onto our vector V of our vector W was going to be V dot W divided by V dotted with itself times our vector V. And so in this case, what we want is the projection in the direction of our plane of our gravity vector. So our gravity vector, we said that one was just going to be 0 and negative 5,300 pounds for the car exerting a force straight down. Our vector P, remember, was already a unit vector. That was our cosine of 8 degrees, sine of 8 degrees. And so if we took the projection, that was going to be our vector P dotted with our vector G divided by P dotted with our vector P, and that was going to be in the direction of P. And so what we have for these dot products, we have G dotted with P, was really just going to be negative 5,300 times our sine of 8 degrees, because 0 times our cosine of 8 was going to be 0, and then we had negative 5,300 times our sine of 8, and we add those together, and so we have that our dot product is approximately 737.61744. Because P is a unit vector, we have that P dotted with P is just going to be 1. So if we plug this into our formula for our projection, we have 737.6174 times our vector cosine of 8, and our sine of 8, which was 0.1391731. And so what we have for the projection is negative 730.4389582 and negative 102.6565009. Now, what this is the actual force that's in the plane that is pulling the car down the plane. And so what is the magnitude of the force needed to restrain the car? Well, it is the magnitude of this projection. And so if we take the magnitude of this projection, and we take the square root of the sum of the squares of its components, 737.62 pounds of force to keep the car from sliding down the ramp. Now, when we're doing a vector projection, if we want the component, or we want the vector that's going to be perpendicular or normal to the vector projection, then, so we have, what is this one? It is our projection onto V of our vector W. So here's V, here's W. And so this vector is called the normal vector. It's going to be perpendicular to our projection. And how we get that is really just our original vector W minus our projection. And this will give us our normal vector. So in this case, if we want the vector that's normal to the plane in which the car is sitting, we really just simply do what was our force of gravity minus our projection onto our plane of gravity, which gives us 0, negative 5,300 minus our negative 730.439, negative 102.657, kind of rounding those a little bit, which gives us a vector that will be 730.439 and negative 5,197.343. And so the magnitude of this normal vector, the projection onto P of G, is just going to be the square root of the sum of the squares of these components, so 730.439 squared plus negative 5197.343 squared gives us approximately 5,284.4203 pounds. And so to bring all of this kind of home geometrically, go back to our original picture. We had our force of gravity here that was doing this. This was our black vector heading down. We have kind of what would be our normal vector. So our normal vector is going to be this vector that's perpendicular to the plane that we were talking about there. So that whenever we see it, this was our vector gravity minus our projection onto the plane of our vector gravity. So this vector, the red vector, gave us our normal vector, and so in terms, it's kind of our components. We can see that it's heading down, but then it's also heading kind of to the right of our vertical and horizontal in our picture. And so it makes sense that our horizontal component of our normal vector was positive, and the vertical component for our normal vector was negative. And finally, for our projection itself, this was our blue vector up here that showed up in this case. This was our projection onto the plane of our vector of the force of gravity. And so kind of putting all three of those together, what we have is that if we do our normal vector and we do our projection vector, then we get back our vector that's going to be our gravity vector that shows up here. So I hope this has kind of illustrated how the components that go into this particular problem, and I will see you guys in the next problem.